Okay, so in this video, we're going to talk about the domains of the composition. Most people usually don't have a problem when it comes to determining Fogg or Goff, and I'll write the definition of Goff, which is just the inversion of the f and the g. So this by definition will be g of f of x. So I will put that in there for you to see. And remember, Goff does not necessarily, actually most of the times will not equal to Goff. F composed of g will most of the times not equal g composed of f. So just keep in mind when you're working these through that these two will not necessarily equal. So more specifically in regards to the domains, we say here is the definition where x is in the domain of g, and that's an and g of x will be in the domain of f. So let's talk about what this means. So let's discuss this with an example. So let's look at an example. We'll say let f of x equal to, we'll say square root of x, and g of x equals to, we'll say x minus 4. X minus 4. So let's say in this example we want to determine f composed of g of x and its domain. So this should be no problem for us. Where it gets a little bit more complex is when we discuss the domain, but don't worry, we can handle it. So let's look at f of x. F of x is a radical function, specifically with a 2 index, which is even. Therefore, we know that the radicand must be greater than or equal to 0. So we can write this as x such that x must be greater than or equal to 0 in set notation or in interval notation from 0 to infinity. If we look at g of x is equal to x minus 4. We should all recognize this guy is a polynomial. He is a polynomial. He's a linear polynomial. We know the domains of all polynomials are all real numbers, which can be written in interval notation from negative infinity to positive infinity. So the way that I like to analyze this is that I like to remember my f composed of g. I like to remember my Fogg, what it really means. So if I look at this, this is really equal to f of g of x. This g of x right here, I like to call the inception function. I don't know, I just came up with this. This is the way it helps me remember. I think of the inception, I think at the beginning, the commencement, that if this function does not exist at the very beginning, we can't even go and plug it in. So I automatically think to myself when I'm doing this, what is the domain of my inception function? So I have f of g of x like such, and I look at g of x and I say, okay, this is a really nice domain. It's all real numbers. I love working with all real numbers. So I'm just going to make a little annotation here that I have a domain of all real numbers because we're going to use this domain to overlap or intersect it with the domain of my final composed product. So this is going to be f of g of x, but g of x is equal to that x minus 4. And again, this domain is still negative infinity to positive infinity. We love working with those domains. And now everywhere in f, I see an x, I'm going to plug in my inception function. So I'm just going to be plugging in x minus 4. X minus 4. So now I have to analyze. We have to analyze the domain of the final simplified composition. So here we're going to analyze the domain of the final simplified composition. So we have that square root of x minus 4. So this is a radical with an even index. So we know the radicand must be positive. So we add 4 to both sides, and we get x must be greater than or equal to positive 4. So that's the domain of our final simplified composition. So now, when we talked about earlier, where we said, okay, where x is in the domain, of g, so let me bounce back down here, where x is in the domain of g, and g of x is in the domain of f, what that really means is intersect the inception function domain. So the final domain, so make a little note here for final domain. So determine the intersection of the inception function's domain and the domain of the final composition. So that's what that translation, that formal definition of the domain of the composition, that's what that translates into. So let's go ahead and look at this. Let's look at this. So we need to determine where the inception function's domain, which I love, is negative infinity to positive infinity. So we're going to look at where does negative infinity to positive infinity, where does that intersect? Intersect is known as the upside down U. Where does that intersect with x must be greater than or equal to 4, which is the same thing as me writing 4 to infinity inclusive. So where do these two overlap or intersect? And clearly, if you overlap 4 to infinity with all real numbers, you're going to get the answer must be from 4 to infinity. 4 to infinity, because whenever you lap anything with all real numbers, you're always going to get that anything. So the domain of f composed of g is in fact 4 to infinity. They will get slightly more complex. But nothing that we can't handle. So let's go ahead and try another example. So let's go ahead and say that we're given f of x is equal to 1 all over, let's say, x minus 4, and g of x is equal to 3 over x. So I'm going to ask you to determine f composed of g of x and g composed of f of x and their domains. So the first thing that I like to do is that I like to recognize the domains of my independent functions. So with f of x, we hopefully recognize that f of x is a rational function. With all rational functions, we know the denominator can never equal to 0. Therefore, we know that x can never equal to positive 4. So we would write this domain as x such that x can never equal to positive 4. You could write that as negative infinity until 4. Not inclusive, joining that with 4 to infinity. But again, I much rather use set notation than interval notation. I find it a lot more expeditious. Looking at g of x is also a rational function, and his domain will be setting the denominator not equal to 0. So this will be clearly x cannot equal to 0. So the domains of f and the domains of g are very different. But we're going to use them because we're finding the composition of each individual function. So we're going to say this will be negative infinity to 0, union 0 to positive infinity. So now let's go ahead and find f composed of g of x. So let's go ahead and find f composed of g of x. And I'm just going to keep this here. I don't want to lose it as I scroll down the page. There we go. So if we want to find f composed of g of x, this will give me f of g of x. So this right here is my inception function. So I'm thinking to myself, what is his domain? His domain is we cannot equal to 0. So my final composed function will have to have a domain that intersects where the domain will intersect this value, x cannot equal to 0. So now we're going to have f of g of x, but g of x is 3 all over x, and that's going to give me 1 all over, I'm plugging in here, so I'm going to have 3 over x minus 4. In order to subtract a fraction, you must have a common denominator, which is in fact a value of x. So this will give me 1 all over 3 over x minus, this is a value of 4, but I have to have a common denominator, so hopefully we all recognize it's going to be 4x all over a value of x. So my common denominator is a value of x, and once we have a denominator that's common, you can subtract the numerators, and this is one of those complex fractions because you have a fraction within a fraction. So we have 1 all over 3 over x minus 4x all over x. Go ahead and combine that. And we're going to have 1 all over 3 minus 4x divided by x. So now, whenever we divide 1 by a fraction, we flip and invert. So flip and invert. So this is really the same thing as me saying 1 divided by 3 minus 4x all over x. And we are going to change our sign to multiply, flip, invert. Flip, it should be flip and invert. Yeah, flip or invert, they're the same thing. Flip and invert mean the same thing. So I think I was saying that because if you flip and invert, that's just negating yourself. So we're just going to flip, also known as inverting. So this will give you x all over 3 minus 4x. So this right here is my final composed function, but I still have to find the domain. So now I have to look at the domain of this guy. And this guy is also rational, so we have to set 3 minus 4x not equal to 0. I'm going to add 4x on both sides, and I get 3 cannot equal to 4x. Divide both sides by 4, and we get x cannot equal to 3/4. So now we have the domain from my final simplified composition and the domain from my inception function. So where do these two overlap? They overlap where those two values are excluded. So the domain of f composed of g of x is all values of x such that x cannot equal to 0 and 3/4. And you could write that in interval notation. It's a little bit more cumbersome, but we would write this as negative infinity until 0, not inclusive, union 0 to 3/4, not inclusive, union 3/4 to infinity. So each one of those is a valid way of writing the domain. So you have to find the intersection of those two values. So let's go ahead now and find g composed of f. We'll do it a little bit faster since the video is running a little long. So we're going to find g composed of f and his domain. So g composed of f and his domain, which is the same thing as me saying g of f of x. G of f of x, I'm thinking, what is the domain of f of x? It is x cannot equal to 4, so that's the inception function. So whatever I get for my final domain, I'm going to have to intersect that with x cannot equal to 4. So this is the same thing as me saying g of f of x, but I'm going to have 1 all over, I'm going to have 1 all over x minus 4. And this will now be plugged in everywhere I see an x in g. I'm going to plug in 1 all over x minus 4. And notice now I have 3 divided by 1 all over x minus 4, which is the same thing as me saying 3 times x minus 4 all over 1. This is in a set of parentheses, even though we don't see them. So this will give me 3x minus 12. And this guy is a linear polynomial. He's a linear polynomial, so his domain will always be negative infinity to positive infinity. So now, where do we have our domain of g composed of f? It's going to be the intersection of our inception function domain, which is x cannot equal to 4, and the final composed function, which is negative infinity to positive infinity. So where do they intersect? It's going to be where x cannot equal to 4 and any other value. So the domain of g composed of f of x is going to be equal to x such that x cannot equal to positive 4. We love working with polynomials or whenever functions simplify to polynomials because they have domains that are very easy to work with consistently. So our final domain is x such that x cannot equal to 4, and our composed function is 3x minus 12.